So 잘 들리시나요? So can everybody hear me? Maybe not. Yes. 네, 감사합니다. Thank you very much. Okay, so let's start today. And let me share the screen. Activate checkbox. So just like before, anytime if you can really follow what I'm talking about, I mean, you can just ask anything. So you can just say, please explain certain things again. That's also completely, very good question as well. Okay, so here's what we are doing right now. So we are studying something called Lambda Calculus. Which provide the foundations of applicative or functional programming languages. More precisely, most of the programming languages nowadays have good support for defining high-order functions and then using them. And Lambda Calculus help us to understand what's really going on by those programming language constructs. So last time we talked about, so here's a reminder. So we studied the syntax of Lambda Calculus. The syntax was really simple. It consists of expressions, but expressions are just variables, or Lambda abstraction, which is really correspond to defining functions. Okay. And then the third possibility is applying function, which is called application. And then we look just like in any other languages that we studied before, we define some operations like the notion of a free variable and notion of substitutions, and applying the substitution on this language, on expressions, Lambda expressions in this language. And then we studied about so-called alpha equivalence. And then the notion alpha equivalence is nothing but equivalence relations on expressions in this language where what we can obtain one term from the other by renaming Lambda bound variables. For instance, one example of alpha equivalence was like this. And this is alpha equivalent to lambda. Okay, this is okay. That's okay. That's because we can obtain the term on the right-hand side from the term on the left-hand side by renaming bound variable x to z and bound variable y to y prime. And the reason we studied about alpha equivalence is because everything we are going to do, they are, in fact, more precisely, they are about alpha equivalence classes. So we are not really distinguishing two expressions in this language, or two programs in this language that are alpha equivalent. There was a syntax and then basic operator. But important bit that we studied a little bit after the half of the last time's lecture was about the notion of contraction and the notion of reduction. And contraction and reduction, they are binary relations on expressions. And then reduction is defined by reflexive transitive closure of contraction and also closure with respect to alpha equivalence classes. So, and intuitively, this contraction describes a one-step computation, reduction describes multi-step computations. But the computation that is allowed in this contraction relation is very permissive. It's much more than what we normally view as computation steps in typical programming languages. And we specify this contraction relation in terms of the inference rules. So here are three inference rules that we studied. So there was something called beta reduction, which say if we have lambda x dot e prime, that's gonna be contracted to e where x is replaced by e prime. So that's a beta reduction. And then there were two more things. One is called alpha, I think it's alpha equivalence. Actually called renaming. And that renaming say if we can go from e to e prime, and then e prime and e double primes are alpha equivalents, then we can go from e to e double prime. So really renaming say we are this contraction relation is with respect to alpha equivalence classes. And the final part is so-called contextual closure. Which say if we are given E, we can go to E0 to E1 prime. If somewhere inside the E, we have an occurrence E0. So in E0 prime, somewhere inside the E0 prime, there is a single occurrence, some sub-expression called E0. And then E0 can go to E1 by the by rules that we are defining right now. And then if we replace E0 by E1, that's going to be E1 prime. In other words, we can apply contraction relation to any sub-expressions in E0 prime. That's what the contextual closure is telling us. Okay. So these are the relations, the rules that define the contraction relation. And then the contraction relations, it's a reflexive transitive closure, also closure with respect to alpha equivalence classes, leads to the reduction relation. And then we ask the following question. Because this contextual, this language is very deterministic. There are no like a random choice or non-deterministic choice operator in this language, except we have a contextual closure. So the contextual closure can be applied to any sub-expression in any order So that raised the question whether if we contract given lambda expression, given expressions in this lambda calculus, is it possible that we are going to end up with two different answers? So we looked at the, okay, so some notion called beta normal form. So we say some expression E is a beta normal form if we cannot, so E is not going to be contracted to E prime for any E prime. In other words, as far as contraction is concerned, from the computation is concerned, E is an answer. We can't really reduce it any further. We can contract it any further. So that was a beta normal form. Then there is a natural question, which is, given an E, can we, so let's write it here. So given expression E, so is it possible to get two beta normal forms, two different beta normal form expressions from E using this contraction relation? In other words, is there any inherent non-determinism in this language? Because if we can get two different answers, that means one expression can potentially produce two different outputs depending on which subterm we contract first. Okay, so then at the end of the last lecture, I said actually that the answer for this question is no. And then that's related to so-called charge Rosa. I think it's SSCR, charge Rosa's theorem. Okay, and then another question that I also ask is, for given expression E, maybe write it here. So the second question is, given E, okay, can you always get a beta normal form E prime from E using contraction? In other words, can you always get an answer? And the answer was again no. And this is actually easy to see. I mean, if we define E as an expression of this form, so if we set E to be some expression like this, so then this term we will never be able to contract this to a beta normal form. If you contract this, it's going to be the same thing up to alpha equivalence. Let's see. So in other words, this one is this expression. This can be reduced again and again and again. It can be contracted again and again and again. So the answer is no. So there is a term, or there is an expression in lambda calculus which doesn't terminate. I mean, if we phrase this computationally. The third one is that now, if given E, so if E can be contracted to, E can be reduced to E prime for some beta normal form expression E prime. So then can we find E prime systematically? So in other words, I mean, this relation that I wrote here is very non-deterministic. So it's just that when we apply these context closure rules, pick one sub-expression in a current expression we have, we apply contraction there, right? Especially beta reduction there. And then next time we also pick appropriate sub-expression, apply beta reduction and so on. So it's a very, depending on making all the good choices. But by systematically, I mean, can we write an algorithm if such that if algorithm of choosing this contextual closure rules, such algorithm that knows how to apply these contraction relations in a deterministic way, such a way that if we follow this algorithm, it will be as good as we can get in terms of getting beta normal form. And the answer for the last is actually also yes. And that answer will be something called normal order reduction. This is very much related to so-called normal order evaluation or the call by name evaluations in programming languages. So what we're going to study now first is that we will look at this Church-Rosa theorem, and then also we will study about this normal order reduction. Okay. And then we will then talk about, so, I mean, this one, the contraction relation and reduction relations are very aggressive evaluation strategy. They form the basis of not just a typical runtime system of programming languages, but also they form the basis of many program manipulating algorithms in compilers and verification tools and so on. For instance, notion of symbolic execution, partial evaluation, and so on, they are based on this contraction reduction relation. So they go beyond what's typically done by the real machine when you run, say, Haskell program or Scala programs and so on. So we're going to study about something called normal order evaluation and eager evaluation. They are a restricted version of these contraction reduction relations, but they are much more close to what's really going on in the runtime system of a real machine, of a real programming languages. Okay. So something. Synchronization problem again. So, okay, so let's move to the next. So what we are going to do? Next things we're going to do is Church-Rosa. And unique normal form. So here's a statement of Church-Rosa theorem. This is a very famous theorem. And then there are many theorems of this form. But in our context, it says the following thing. So let E be an expression in Lambda Calculus that we are studying right now. And then suppose that, so it says that if E can be reduced to E1 prime, and then also E can be reduced to E2 prime. Okay. For some expressions, E1 prime and E2 prime. So these are the setting or assumptions of this theorem. The conclusion is that if that's the case, then there exists E0 such that E1 prime can be reduced to E0 and E2 prime can also be reduced to E0. So from what does that mean intuitively? If intuitively it means that from expression E, we apply this contraction rule multiple times, possibly 0, once, twice, or multiple times, but in certain way. And maybe we apply the contraction in a different way by using the contextual closure rules for the different sub-expressions that we encounter in each computation step. Then we may end up with a two different outcomes, E1 prime and E2 prime. But the theorem says, but at that point, if we change our minds and then say, okay, I want to control this, I want to pick the contraction relation more carefully, so that I can end up with the same final outcome, then that kind of a wish can be achieved. So if you picked the contraction relation in the right way, starting from E1 prime, also another right way, starting from E2 prime, we may end up with exactly the same expression E0 at the E1 prime case as well as E2 prime case. Typically, when people state this Church-Rosa theorem, they use a diagram. I mean, this is not a categorical diagram, but this is a diagram that people often use. They write it like this: from E, they said it can be E1, E can be reduced to E1, E1, it can be reduced to E2 by applying this contraction. So then, I mean, this dot 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 means it's exist. So there exists E0 such that E1 can be reduced to E0, I mean E1 prime and E2 prime. And E2 prime can also be reduced to E0. So it's a diagrammatic and rewriting the theorem above. Okay, so this is what typically people do. We are not going to prove this. I mean, I think the proof of this may be non-trivial. So we are not going to prove this, but we're gonna do the following, which is that now using Church-Rosa theorem, we can prove that this unique beta normal form statement. Okay, then let me put the right number there. So I think this is called proposition 10.3 in the textbook. So that proposition 10.3 said, if expression E get reduced to E1 and expression E get reduced to E2 for beta normal forms expressions E1 and E2. If that's the case, then E1 is alpha equivalent to E2. E1 and E2 are alpha equivalent. So this proposition can be proved by using Church-Rosa. So I will give you 3 minutes to, I think the best way to digest what's really going on is really think about it for yourself. So here's the proof. So here's an exercise for you to do. So I will give you 3 minutes to try to prove this proposition 10.3 by using Church-Rosa theorem. Okay, so let me show this. The proof is quite simple. So, okay, by assumptions, we know we have a E by assumption. E goes to E1 by reduction. E also goes to E2. Now by Church-Rosa, there should exist E0 such that E1 get reduced to E0 and E2 also get reduced to E1 and E0. But now E1, we know that E1 and E2 are in beta normal form. So we cannot contract E1 and E2. So the only possibility that we can have when we have something like this E1 get reduced to E0, E2 get reduced to E0. The only possibility is that E1 has to be alpha equivalent to E0, and E2 also has to be alpha equivalent to E0. That's because this relation, that the arrow star, is alpha equivalence and reflexive transitive closure of contraction. Because we cannot use contraction at all, E1 and E0 should be essentially the same. Okay, and then here the notion of same means alpha equivalent because this is defined with respect to alpha equivalence clauses. So what does that mean? That means if we have this E1 is alpha equivalent to E0, E2 is alpha equivalent to E0. And alpha equivalence relation is an equivalence relation. So if E1 is alpha equivalent to E0 and E2 is alpha equivalent to E0, so that means E1 and E2 are alpha equivalent. So that's exactly the claim of this theorem. So we can prove this theorem quite simply. Okay. So key step is we use by Church-Rosa, we derive this, but because it's a normal form, and the relationship that we derive from Church-Rosa has to be, in a sense, very degenerate. I mean, only for the base case. So this Church-Rosa theorem and then correspond the following proposition 10.3 say that lambda calculus, there are no inherent non-determinism. We will get either no answer or we will get exactly one answer. Of course, if we follow the adopt a strange strategy, then the reduction may go on forever. But if you choose the right strategy, reduction will produce, if it's possible, produce only one beta normal form answer. So then the next question that we want to answer here is about the systematic strategy for getting a beta normal form. So this is called normal order reduction. I think the best way to understand the normal, so this is a particular way, it's a particular deterministic, or you can say it's an algorithmic way of applying contraction relation. Okay, so I mean this normal order reduction we sometimes call normal. This is as a binary relation between expressions. I think it's written like this. That's gonna be a subrelation. So only certain reductions are legitimate according to this normal order reduction. Okay, so to understand this, I think the best way is to actually look at some example. So think about this example, U and V. X dot XX and lambda X XX. Okay, So for this expression, if you compute, if you look at the first radix, the outermost radix here, and then reduce it, then you will get a very simple answer, v dot v. That's because the body of the lambda abstraction is lambda v dot v, where the parameter u doesn't appear. So if you apply beta reduction, that's what we're gonna get. But if you apply the beta reduction to the argument here, so to the arguments, so in that case, we end up with exactly the same thing. So this means that if we apply follow exactly the same strategy, we can essentially get the same thing again and again and again, and this can go on forever. So what this example suggests is that depending on which beta radix we reduced first, in this case, like a red one that we pointed out, or a blue one, I mean, we either get a beta normal form, or we may end up with reducing the contracting the given expression again and again and again forever. It will never terminate. So the question becomes, which ones, how should we systematically choose beta radixes to contract next, so that if it's possible to get the beta normal form answer, we can always get it. In other words, what's the systematic way of applying contraction that will give us as much answer as possible? And then it turns out there isn't one answer, maybe multiple, but there is one very well-known answer. The answer is the normal order reduction. So, in a sense, we can say it's the best in terms of getting beta normal form answers. Okay. So it will let us avoid this non-termination as much as possible. So then what is it? So it is defined in terms of like this. Is normal order reduction is sometimes written as leftmost and outermost reduction. Or, I mean, according to the terminologies, maybe contraction is a better way to say this. So what does this leftmost, outermost means? So in this example, now let's compare two beta radixes that we have. One beta radix is the red line, and then the other beta radix is the blue one. But if you look at the blue one, that is included inside the outer beta radix. Just beta radix here, include everything. Outer beta radix, okay? So this normal order reduction say, if we are in such a situation, always reduce the outermost one, the beta radix that's not going to be included in any other beta radixes. For instance, in this example, this blue one, we are not going to reduce it. Okay? So that's the first things this normal order reduction is telling us. So that's what this outermost means. And for leftmost, I think the best way is look at the example. If you have a multiple beta radixes, which are all outermost, evaluate the leftmost one first, okay? So example is that if you have a beta radix like this, it's a very silly one. I suppose you have a this is a very silly expression, but Now, if you look at this, I mean, this topmost application here, this is not beta redex. Why is that? That's because the argument, the operator part is not a lambda expression. Okay, so that's why it's not a beta redex. But we have a two beta redices here. The first one is this beta redex in the operator position. Another, the other beta redex in the operand position. Okay, so we have two beta redexes. They are not in this nested relationship at all. So this outermost criteria doesn't really tell us which one to contract first. But in such a situation, normal order reduction say pick always the leftmost one. So if you follow this leftmost reduction strategy, then we reduce this one, the argument one first. So then we end up with lambda y dot y, and then lambda x the y dot y. In the second step, I mean, the right-hand side beta redex, it used to be outermost, but no longer it's outermost because now the operator part is a lambda expression. So we have to, in this case, reduce the entire beta redex. They will give us an answer, which is lambda x, lambda y, y. And then now we have yet another beta redex. If you reduce it, they will give us an answer, lambda y, y. So that's how the normal order reduction work. It just specify the choice of beta redex. So, and then the normal order reduction say always pick the leftmost and outermost one. Then the theorem is that, so if you write this, I mean, this is a specific way of using contraction relations. So if you write contraction relation according to normal order like this, and corresponding is a reflexive transitive alpha equivalence closure as like this. So then here's the theorem. So the theorem say if we can somehow find a way to reduce expression E to E prime for beta normal form E prime. So then E can be reduced by normal order and to the exact same answer E prime. So if it's possible to get a normal, the answer, then following this beta, the normal order reduction will give the answer. Now, another point which is that this normal contraction is deterministic. So modulo, I mean, this alpha equivalence relation. So there are no ambiguities about which one to evaluate next, which one to contract next. That's because this leftmost and outermost really fix which beta redex we have to contract next. The original, you go all the way back, all the ambiguity in the contraction relation, they came from, so we have three rules in the contraction relation that they really came from this contextual closure. Because this contextual closure tells us, I mean, if we can, I mean, really, if you combine all of them together, the contextual closure say, given E0 prime, pick any beta redex in B0 prime, which is any sub-expression, which is beta redex in E0 prime, and contract this. But the normal order evaluation say, oh, you can't really pick anything. You always have to pick leftmost and outermost beta redex. So it really fixes how we should use this contextual closure rule. So that's why to make it very deterministic. So you can, I mean, although we are not asking you to do it, if you want, you can design some program that really implements this normal order reduction. Okay, so here's another synchronization problem. Okay, so that's perhaps closes our discussion about the contraction and reduction. So now I'm going to move on to the next topic, which is evaluation. So I think these distinctions among contraction, reduction, and evaluation are perhaps, I mean, there's a John Reynolds' particular convention that he used throughout the textbook. And so typically, if you read a paper on the programming languages, they don't make such a distinction, but it's a good distinction to be made. So evaluation is really a very restricted version of, I think really it's a reduction that corresponds to the runtime of a programming language. Okay, so then the natural question is that, okay, where do this restriction really coming from? So why can't we just use this contraction, which seems to be a legitimate way of implementing this idea of function application? Okay, I mean, all this contraction does is that if you have a function applied to an argument, you just replace the formal argument by the actual values, parameter values in the body of the function, and continue to run the body of the function, which is exactly your understanding about how the function call happens. But then so it looks like this is, I mean, something that you don't really need to restrict again. But there actually, in the real programming languages, there are two types of restriction that happens. The first restriction is that, so which restriction? So the first restriction is that in a programming language, we only evaluate a program that is closed, okay? So only evaluates expressions without free variables. So this expression without free variables, they are called closed expressions. So for instance, if you write a Python program, and then, or maybe in Java program, then if you use variable X without really declaring it, I mean, Python it may work, but in Java, if you write a program without declaring and using X without declaring what X is, then it just won't compile. The compiler will complain. In dynamic language, it will fault, okay? And so what it really means is that whenever we are running program, we run program when it is completely ready. So in terms of the defining all the variables that appearing in the program. So so that's what this corresponds to the step one. Of course, the compiler optimization and strange things like symbolic execution and so on, they go beyond what's really going on, what I just told you. But typical runtime only runs programs that are closed, that do not have any undefined variables, or undeclared variables. So that's one restriction that we should respect and in some sense exploit. The second thing is that we don't evaluate the body of a function unless the function is applied. So if I use the Lambda expression to explain what's going on here, so if I write a function like this, lambda x dot lambda y dot y applies x. Okay, so this lambda x means that I'm defining a procedure, okay, anonymous function lambda x using Python or Java, and inside the body I define another lambda expression and apply it to x. Okay. According to the contraction or reduction relation, we can contract this to lambda x dot x by reducing the beta red x inside the body of this the lambda, even though this procedure, the outermost procedure, is not applied to anywhere. That's not what's really happening in the typical programming languages. You are defining programs, you are defining some procedure, unless that procedure is applied to something, what's written inside the procedure will never get evaluated. So this is another aspect of a runtime system of programming languages. I mean, you might say, okay, these are just restrictions, but actually these are the restrictions that help to develop very efficient runtime of these programming languages. So what we want to do, really the study about programming languages is a study about the runtime system of programming language, study about what kind of properties every program can be written in this programming language have, and so on. So we are studying meta property about the programming language and its runtime. And so we want to formalize this notion so that we can study about what kind of consequences these restrictions really bring. So the formalization is done by two things. Done by something called evaluation relation. So we're gonna write evaluation. There's some new notation that's written like this. And then this is a notation between expressions. But we will define it using, we will define two ways, and they are going to be equivalent. We will define it using the contraction that we just, the reduction that we just defined, but also we will define it separately. So, and then they are both equivalent. So that's what we're gonna do. And then this evaluation relation really captures this number 1 and 2. So what does this mean? For the number 1, it means that it will be on number 1 and 2, especially number 1. It means that it will only be applied to closed expressions. And number 2 means that it's going to be less aggressive than the contraction relation. It's not trying to it will not try to reduce, but to contract anything that's under the lambda, unless we are applying this lambda abstraction to some argument. Okay, so it will capture number 1 and 2. So from above. But the other important bit is that it will, I think this is some decision John just made in the textbook, but this is another important bit that John Reynolds did is that it described so-called the big step computation. In other words, it's not describing what's really happening in a single step computation, but it describes what's going to be the ultimate output that we will get by following certain evaluation relation. So let me just define this first and then tell you what they are. So we're going to define two evaluation relation. One is called normal order evaluation relation. That is related to normal order reduction that I just told you. And the other one is called eager evaluation relation. And this eager evaluation is related to so-called call by value. So normal order evaluation. So we we will often omit this word evaluation. That's going to be written just like here, double arrow. And let's write it with subscript. So how is it defined? So it's defined between, say, closed expressions. I write informally like this: expression without any free variable, and then closed expression. Okay. And then it's defined like this. So it's a let me just first define this first using this independent definition, and then so on. I think let me change this. So it's defined in the closed expression and something called the canonical form. So then this closed expression is just expression that doesn't contain any free variables. Canonical form expression, which I'll just write it as just can. I think maybe C form is better. So this canonical form is just a lambda expression, variable to expressions. Okay. So what does this mean? This indicates that this normal order evaluation relation, however it is defined, it's describe a relationship between closed expressions and lambda abstractions in the lambda calculus. And implicitly, what does it tell us is that given the closed expression as which we want to evaluate, the only possible output that we can get, but the only possible answer that we can get by doing this evaluation is only going to be the lambda expression. So that's what this the form is telling us, and it is defined like this. It's defined by so this is called canonical form. So it's not a normal form, and we identify this canonical form because of this number 2. Okay, we are trying to describe a computation. No, not this number 2. So number 2 on the top. So we are trying to capture the computation which do not evaluate the body of functions unless the function itself is applied, which means that lambda abstraction is in a sense, if we just have as it is, it's the final answer of what we are going to get. So that is a bit less, it's not as much reduced as the beta normal form, but it's something that's as much reduced as possible according to this evaluation strategy. So that's why we are identifying this specific kind of expression called this lambda expression as a canonical form. And in some description of programming languages, they identify this kind of thing as value expressions. So beta normal forms are the ones that are contracted as much as possible in everywhere. And these value expressions or canonical form expressions are the ones which are contracted as much as possible without really contracting anything inside the body of the function, unless absolutely needed. Okay. So how it's defined? And it's defined essentially the same way as the normal order reduction that I told you, except that inside the lambda, under the lambda, we are not really applying. So the body of the lambda expression, we are not really doing any contraction at all. Okay. So we have two rules. The first rule is called canonical form. So this one say, if we have a lambda x lambda expression, and that's gonna be reduced to itself, and evaluated to itself. As I said, this normal is not corresponding a single contraction. Is more corresponding more to this multiple step computation formalized by reduction. So we said, if we have a canonical form, don't do anything. That's the final answer that we already got. So we just return it. For function application, we have another rule called application, or sometimes called as a beta evaluation. So we say that if we have a lambda x dot e applied to e prime, lambda x dot e. So if you have an application in the language, then we first evaluate the operator to get a canonical form. But canonical form is always going to be a lambda expression. So we get a canonical form. And then once we get a canonical form, we look at the body of the lambda expression and replace the former parameter x by actual arguments. So maybe and then continue the evaluation, and that will reduce some answer. And then in the textbook, John is using Z to denote the expression of the canonical form. So that's going to be the final answer in this case. And so this normal order evaluation is formalized by these two rules. So just applying these two rules that will help us to do the evaluates the expressions according to this normal order evaluation. So let's apply this and see some example. So we have lambda x, lambda y, x, just the same thing. Y dot y, and then apply to C dot c. And suppose we have an expression like this. So then we want to evaluate this one. Then by the rules of the application, maybe I can select. No, it doesn't. So I need more space. So let me. Okay, so let's look at. So if you look at this example. So we first evaluate the operator, which is lambda x let's make it more interesting. Say x, x, the y, x. But this is a canonical form, although it's not a beta normal form because the body has a beta radix, but it's a canonical form because it's a lambda expression. So if you evaluate this normal order, that will reduce to, this one will return exactly the same expression. Okay, so that's why we got it in the first step. And then the second part of this rule tells us now you take the body, which is the body here, and replace x by its parameter. So replace x by the parameter is lambda z dot z. So that we do so, then we will have lambda y dot y, lambda z dot z. So we have to then do the evaluation again for this guy. This one is again the application. So we have lambda y. Look at the operator that's already in canonical form. So it's a lambda y dot y. And then for now, if you replace the argument, which is the body, which is a y, and then argument is this variable y, and replace this the bound variable y by this parameter or operand, then we will have lambda z dot z. So we replace this y by lambda z dot z, so then we got lambda z dot z. And then if we evaluate this, then this is a canonical form, then so we get an answer here. And that's going to be the answer below. And there will be the answer for the everything. So here's the how this we can apply these inference rules. Okay. So, but then you can also, I mean, you can, so then you might ask, okay, so here we are defining some relations from scratch. Is it going to have any relationship with, I mean, this reduction relation that we defined before? And actually, you can do it. So you can say, given a closed expression, so I mean, any relationship between this normal and the reduction. So the answer is yes, there is. And so what happened is that now if you restrict, think about this one with under normal order reduction, but without contracting inside lambda. Okay. So normal order, what is it? It is say that contract beta radix leftmost and outermost manner. Okay, so that's the strategy that we are adopting. And we put one more constraint, which said if some beta radix is inside the lambda, then do not contract it. So we make this normal order reductions more restricted. So let's call this as just NC. NR by means normal order restricted. So then we can prove some theorem. So which is proposition 10.6. So then the proposition in the textbook tells us for any expression, so if we can go from expression E to this N, so normal order but restricted, NR, to some canonical expression Z, if and only if he can go to normal order Z. So they are talking about the same thing. So this is for closed E and canonical Z. So really, I mean, the proof is not that simple, but I encourage you to look at it because it's really a way, I mean, it's not the main point of what I'm talking about, which is about this normal order evaluation. It's something that shows how you can connect the description of computation done for the small step, which is this case, and description of computation done in a bigger step. But but if you don't like it, you don't have to look at it. But just point I'm making is that what we are defining is we directly formalize this normal order evaluation, but that corresponds to the contraction that we defined so far. We are putting one more, we are taking normal order contraction or normal order reduction strategy, but we are putting one more constraint, which say that we are not contract under the lambda. Okay, so that's the normal order. Yeah, so that's a normal order evaluation. So, and then this normal order evaluation form the basis of right. So this normal order evaluation forms the basis of, say, Haskell, and then some mechanism of Scala. Scala is not based on normal order evaluation, but Scala also supports some aspects of normal order evaluation. Okay, so, but that's not the only option. The only way of evaluating a this program that support the high order procedures and so on. There's another very well-known approach, which is called eager evaluation. Four. So yeah, eager evaluation. So that's written like eager. And that's again between closed expressions. And canonical form. C form. So between canonical form. But this ego, let me just show you some, motivation behind this ego evaluation. If you look at this, the expression of this form, so then there is a radix, which is applying this lambda y dot y to lambda z dot z. And now if you do the, just repeats what's going to happen, or follow the rules of this normal order evaluation, then you can check the following thing, which is to check how many times we're gonna reduce what we're gonna contract this beta radix that we see here, lambda y dot y applied to lambda z dot z. Now, in the normal order evaluation, there will be more steps, but this particular beta radix is going to be reduced twice. Why that is the case? Because it's not going to, the key idea of a normal order evaluation is that whenever you look at the argument, you are not evaluating the argument, we are just applying the functions only when we are really needed. That's the time we're going to do the evaluation. So if you do this normal order reduction here, this argument will be plugged in for the first x and the second x without in the form that's written right now. And then, so for the first x, we have to do one contraction step, or one beta reduction step. Second radix, we have to do another contraction step. So you may ask, this is wasteful. I mean, we are really doing many contractions, then that correspond to the wasted number of computation. Can you do a little bit better? So that's one natural question you can ask. Also, it turns out if you implement a programming language based on the normal order evaluation, like Haskell, I mean, things are becomes, the old days, it was very difficult to have a very efficient implementation. Now, I think this is not quite true. We can have efficient implementations, but still, it becomes sometimes quite counterintuitive. The behavior of a program, understanding the behavior and reasoning about performance of the program becomes really difficult. So this ego evaluation is another much more popular strategy of the evaluation strategy adopted by programming languages like OCaml, Scala, Closure. I mean, the Java, most of the programming languages adopt this ego evaluation. And I mean, that's because it's more efficient in some sense, and then it's easier to understand what's really going on. So then high-level idea, high-level idea of normal order evaluation is when you see the function application, do not evaluate argument, just evaluate function code. No evaluation of argument, just evaluate function code. That was the intuition behind normal order evaluation. Ego evaluation is different. We say if you see the argument, evaluate argument before doing the function call. Okay. So here's the rules for normal order evaluation. So it has two rules. The form is for canonical form. That's exactly the same as before. So we say if we have a lambda expression, then ego evaluation. If you ego evaluated, lambda expression is the final answer, so you don't really evaluate anything further. But for I think it's a ego beta or what's the name? Let's call beta E evaluation. So if you have a function call E0, E1, evaluate under eager. So in the normal order case, we evaluate operator to get canonical form, which is a lambda expression. And then we apply the arguments to the body to this function directly without evaluating E1. That was what happens in the normal order evaluation. Here it's different. We are evaluating the arguments to get the canonical form Z. So we write Z because, I mean, it's going to be lambda, but we don't care about what it is. So we just write Z. And then we do the function application. And then I'm going to get a final. So get the final answer here. And the final answer will be given here. So the key difference is this step. You can see the operator, operand evaluation step or argument evaluation step in the ego evaluation. Compare it with this beta evaluation of the normal order evaluation. You can't really see this. So you can see that this argument is passed directly without being evaluated. So that's the key difference between these two strategies, two evaluation strategies. And then this second evaluation strategy has a less nice characteristics in terms of theoretical characteristics. For instance, if there is so let me just mention a few things and then close. So these are the two mainstream evaluation strategies for function calls. And then there are mention a few things and then close. But the first thing is that, I mean, typically it's very difficult to compare which one is better. I mean, in terms of the reduction or contraction step, which one is better? It sometimes works. Usually the ego evaluation works better, but the lazy evaluation sometimes perform better because if you don't use an argument, then the lazy evaluations doesn't do any the beta contraction or beta reduction at all. So in terms of the performance, performance. In terms of number of evaluations for beta E evaluation steps. So there is no clear winner. Clear theoretical winner. But in terms of understandability, it's a very informal word. I mean, which one is easier to understand what's going on? Actually, my feeling is that actually kind of what I think is ego evaluation is much easier to understand. Even without following this rule, you can see that okay, what should be the outcome, and also you can analyze how many steps are involved and so much more easily. But then you might ask me, why not using ego all the time? So then there's a theoretical property. In terms of theoretical property, normal behave a lot better. So just like a normal order reductions that we talk about, so we talk about this normal order contraction and normal order reduction. We said this normal order contraction have the property of if it's possible to get a beta normal form, normal order will give us. And this normal order evaluation have the same property. If it's possible to get, for some case expression, normal order can give a canonical form, but ego may fail. And if ego gives us an answer, normal always give the same answer. So normal can evaluate more than ego. Okay? So that's some nice theoretical property, and some semantics will become a bit simpler as well. But in practice, the ego is something that's, in a sense, preferred because it's much easier to understand and analyze. Okay, so that's it for today. And next Monday, this Wednesday, I'm going to talk about the semantics, and that will close our discussion on the Lambda Calculus. Okay, so thank you very much for attending the lecture. If you have any questions, feel free to ask me. I'll be around for about 5 more minutes.